What happened? Okay.
Yes, that's fine.
Okay, so the first question is, ammonia is burned to form nitric oxide in the following equation, this equation. And question A, calculate the ratio per mole of oxygen reacted over per mole of nitric oxide formed. So we need to find the ratio of mole of oxygen consumed to the mole of nitric oxide formed by dividing the stoichiometric coefficient of oxygen by that nitric oxide. So it's going to be 5 per mole of oxygen reacted over 4 per mole of nitric oxide formed. And the answer is 1.25 per mole of oxygen reacted over per mole of nitric oxide formed. And the question B, if ammonia is set to a continuous reactor at the rate of 100 kilomole of ammonia per hour, what oxygen feed rate in unit of kmol per hour would correspond to 40% excess oxygen? At first, we have to find the amount of oxygen that we need to react with 100 kilomole of ammonia. So the amount of the oxygen equals to 5 kilomole of oxygen over 4 kilomole of ammonia multiplied by 100 kilomole of ammonia over hours. And we do the conversion and so the answer is 125 kilomole of oxygen per hour. After we get the amount of oxygen, then we multiply it by 40% excess of oxygen. So 40% excess of oxygen is equal to 100 plus 40 over 100 is going to be 1.40. So the number of oxygen feed rate is going to be 1.40 times 125 kilomole of oxygen per hour. So the answer is 175 kilomole of oxygen per hour. And the question C, if 50 kilograms of ammonia and 100 kilograms of oxygen are fed to a reactor, first we want to find the limiting reactant. We have to convert the initial masses of the reactant to kilomoles by using their molecular weights and divided the mole oxygen by that ammonia and compared to the stoichiometric ratio of the chemical equation. So for the ammonia, 50 kilograms of ammonia times 1 kilomole of ammonia over 17 kilograms of ammonia, which is ammonia molecular weight. So the answer is 2.94 kilomole of ammonia. And for the 100 kilograms of oxygen times 1 mole of oxygen over 32 kilograms of oxygen, which is molecular weight. So the answer is 3.125 kilomole of oxygen. And so the number we get is 1.06, which is less than 1.25 stoichiometric ratio from the part A. So the oxygen is a limiting reactant and ammonia will be in excess. And then we need to find the percentage by which the other reactant is in excess. We have to find the amount of ammonia needed to fully reacted all of the oxygen, then subtract this required amount from the actual amount present, and then divided the result by the required ammonia to find the present excess. So the required ammonia is 3.125 kilomoles of oxygen times 4 mole of ammonia over 5 mole of oxygen. So it's gonna be 2.50 kilomole of ammonia. And then the percentage of excess ammonia is 2.90 minus 2.5 over 2.5 times 100. So the answer is 17.6% of percentage of excess ammonia. And next, we want to find the extent of reaction. So solve the extent where the mole of ammonia is the stoichiometric coefficient of the ammonia in the chemical equation. The number of ammonia minus the number of ammonia plus the required ammonia. Again. So the number of ammonia minus required ammonia equals to the amount of ammonia plus mole of ammonia times the extent of reaction, which is the mole of ammonia is minus 4 because ammonia is a reactant. So the extent of reaction is equal to 0.625 kilomole or 625 moles. And the final, we need to find the mass of nitric oxide produced. So calculate the mass of nitric oxide produced by using the mole variable of the limiting reactant, oxygen, the ratio between the limiting reactant and the products, and the molecular weight of the products. So it's going to be 3.125 kilomole of oxygen times 4 kilomoles of nitric oxide over 5 kilomole of oxygen times 30 kilograms of nitric oxide over 1 kilomole of nitric oxide. So the answer is 25 kilograms of nitric oxide. That's it, Ajahn.
For this question, for frequency, what kind of the limiting reactant? Ammonia or nitrogen? Ammonia or oxygen?
Oxygen.
Oxygen, okay. If we would like to calculate the conversion, would you suggest the technique to calculate the conversion of frequency?
This question,
from the data or information that you obtain from frequency, would you suggest the technique or method to calculate the conversion?
By the same unit. Yes, I think.
Only this time the technique or the method to calculation. Do not calculation, only suggest me the technique or the method how to obtain the conversion, how to determine the conversion.
I think by the same unit as how can I say, at that value. So you can, how can I say, so you can cancel the unit that you don't need to have it. I don't know.
I think you calculate that you use the extent of reaction, you know amount of ammonia outlet the ammonia at the final state of ammonia, and also you can calculate the final amount of oxygen. I think because you calculate put you back the previous slide, slide number 6. Yeah. Yes, for this case you calculate ammonia by the extent of reaction. The output, the final ammonia equal to initial ammonia, but the consumption And also you can calculate ammonia as the output, and also you can calculate the oxygen because oxygen is the limiting reactant. That's right.
Yeah.
And also you can calculate the conversion by the
oxygen.
Initial oxygen. That's right. Initial oxygen minus final oxygen divided by initial oxygen multiply 100, and you get percent conversion. Percent conversion means amount of oxygen convert to the product. That's right. Mostly when you calculate the conversion, you calculate based on limiting reactant. Because this is oxygen limiting reactant. Okay.
Okay.
Okay. Thank you for your presentation. Let's the next.
Okay.
So the next question is post-con, right?
Yes.
Okay, so let's start your presentation.
Let me share my screen.
Yes.
For the question number 2, no, I cannot see. In the decon process for the manufacture of chlorine, hydrochloric acid and oxygen react to form the chlorine and water sufficient is equal to 21 mole per oxygen and 79% nitrogen is fed to the provide 35% excess of oxygen, and the fractional conversion of HCl is equal to 85%. Then for the first question, and here's for the process for chart of the system. 100 moles of hydrochloric acid is the system of the process with the unknown moles of air. Then fractional conversion of hydrochloric is equal to 85%. Not all of it is converted. That means the only 85 moles of HCl is react and another 15 moles is not. And oxygen is supplied in acid 35%. For the nitrogen is go with the oxygen in the air, and chlorine is produced during the process with the water. For part A, we need to use the atomic species balance method to calculate. For the degree of freedom analysis, we have the unknowns of 6 and is equal to 6, A plus 6, and independent atomic species is equal to -3. Independent non-reactive molecular species is equal to -1. And others equation from the excess of oxygen and fractional conversion is equal to -2. Then the degree of freedom is equal to 0. For the calculate of the unknown, let's start from the N1 using the excess of oxygen. That we have to find out how much of moles of oxygen is required to react with the hydrochloric acid using the stoichiometric ratio. Then we got the moles of oxygen is equal to 25 moles. Then we can calculate out that N1 is equal to 160.7 mole. And for the N2, we use the fractional conversion of hydrochloric, which is 85% conversion to calculate to find the N2 using hydrochloric balance. Then we got it equal to 15 mole. Then we using the chlorine balance to find N5. then we got it equal to 42.5 mole. And using the water balance to find N6, then we got it equal to 42.5 mole. And for the next one, N3, we use the oxygen balance. Then we got it equal to 12.5 mole. And the last one is N4. We use the nitrogen balance, then we got it equal to 126.9 mole. And for the mole fraction, we know that the N total is equal to 239.5. Then we can calculate the mole fraction of HCl is equal to 0.63 mole HCl per mole. And the other is for the mole fraction of the other is on the slide. So the next one. For this part B, we need to use the extent of reaction in the calculation. So degree of freedom analysis, we use the extent of reaction method. For the unknown, it's equal to +6. And for the independent chemical reaction is equal to +1. Independent reactive molecular species is equal to -4. And independent non-reactive molecular species is equal to -1. And the other equation from the excess of oxygen and fractional conversion is equal to -2, then the degree of freedom is equal to 0. For the N1 and N2, we use the same method to find out as a previous method. Then N1 is still equal to 160.7 mole, and N2 is equal to 15 mole. For the extent of reaction, we got it as in the slide. Then we can find out that the extent of reaction is equal to 42.5 mole. Then we use this value to calculate in the others. For N3, we got it equal to 12.5 mole. And for N4, it's equal to 126.9 mole. And for N5, it's equal to 42.5 mole. And N6 is equal to 42.5 mole. As the molar quantity are the same as the previous method, then the molar fraction would be also the same as the previous method. That's all, Ajahn.
You're muted, Ajahn.
I forgot to open the microphone. Okay, could you show slide number 7?
Yes, Ajahn. Như này á.
Yeah. For this slide, you talk about the explain operation. I would like to, could you explain in the detail of this equation in terms of mass balance? Could you explain in detail of mass balance? What is Ni, what is NiO, and something like this?
For the Ni is equal to the mole that we want to find out. Then
okay, if I write like the general mass balance in minus out,
yes,
generation minus consumption equal to accumulation. Could you describe the relationship between these two equations? Would you like to any your friend help you? Hong Son, could you understand my question, right?
Yeah, I understand. The minute.
Your technique of the calculation and solve the equation that correct. Okay, that's correct answer. Only try to get your understanding about this equation.
For the generate and accumulation is equal to 0.
Why is it equal to 0?
Then Ni is output. So V is equal to mole of the.
Okay. What is Ni?
Ni. You mean this one, Ajahn?
Yeah, it is input, output, generation, or consumption for Ni.
Oh.
Okay. Lika, could you help Pongsathorn to decide it? Do you have any comment, Lika? Are you hear me, Lika?
Yes, John.
What is Ni? What is Ni?
Ni is the input, John.
Yes. This is not input, it's output. That's right. Oh. This is output. This is output. This is for continuous and for batch should be initial. That's right. Output, how about Ni0? In, that's right. Input. And also term external operation, VI psi. VI psi is mean generation and consumption. That's right. This is output equal to input plus term of reaction. This is term of generation and consumption, gen and con. If the VI for reactant, it should be consumption. That's why it should be negative for this. If the VI is positive, this means product should be generation. This is a positive or negative based on reactant or product. Reactant should be negative. If V is negative, that's why negative. This is for V is positive. That's why. This is the outlet equal to inlet minus generation, minus consumption plus generation. This is the equation. It's the same this, but there is no accumulation for steady state. That's right. Okay, this is the same equation, but we write in terms of this equation for easy to use, but this also come from inlet minus outlet, cut generation minus consumption equal to accumulation. But for this case, we conserve it on steady state system. That's right, steady state system. Okay, thank you for your cooperation, Rika and Foxton. Would you move to the next presenter? I'm sorry, I would like to argue. Are you hear my the noise from my house? Because there are someone around my house is make the agriculture. Do you hear only my or another my the noise?
Yes,
Some noise.
we can hear you.
Okay. Okay, let's start the next question. Who is the next presenter? Carl, okay.
Okay, Ajahn. Yes, Ajahn. So for question number 3, this is the question for question number 3. The gas phase reaction between methanol and acetic acid to form methyl acetate and water takes place in a batch reactor and proceeds to equilibrium. When the reaction mixture comes to equilibrium, the mole fractions of the 4 reactive species satisfy the relation given this relation, and then the chemical reaction is also given. So for letter A, we suppose that the feed to the reactor consists of initial mole of A, B, C, D, and I. And I is the inert gas I, and then we also let C to be the extent of reaction. So we need to write expressions for gram moles of each reactive species in the final product, and then use these expressions and the given equilibrium relation to derive an equation for CE, or the equilibrium extent of reaction in terms of initial mole A, B, C, D, yeah, and I. So first, I'm not sure if this is needed, but I wrote a reference flow chart. So this is the reference flow chart, and then the problem statement says that we need to suppose that the reactor feed has initials A, B, C, D, I. So using this assumption, we can then say that the total feed in the reactor would be equal to N total is equal to the initial mole of A, B, C, D, I. And using this equation, we are then asked to write expressions for G moles of each reactive species. So in other words, this also means to write the N moles as a function of C. So we can then use the general equation of extent of reaction given on the screen, the Ni equal Ni0 PiC. So using that equation, we can then write the following equations for Na, Nb, Nc, Nd. For Ni, we can neglect it since it is an inert gas, and then the problem only asks for each reactive species. So using the previous equations, the 4 equations, we can then use it to express it using the mole fraction given on the screen. So mole fraction is given the general formula yi is equal to initial mole over total mole. So if we substitute it, we can then generate the equation, this one. So after that, we can then use these intermediate equations and substitute it back to the equilibrium relation, which is here already. So now, based on the flowchart, we can then choose for a basis of 1 mole of AB and has no CD at initial reaction. So if we are going to use that assumption, then NC and ND will equal NC0 and ND0 will be equal to 0, and then NA0 and ND0 will be equal to 1. So this will be equal to so this will be equal to C. Sorry, C. I forgot to include it. C1 minus C and 1 minus C is equal to 4.87. So We can then simplify this one by cross multiplication and then expanding. So after everything has been simplified, we are then left with a quadratic equation. So in order to solve the quadratic equation, we can then use the quadratic formula in order for us to have an equation for C. I mean the extent of reaction at equilibrium. So since that is what is asked for this problem, okay. So using the quadratic equation, we can then find that there are two solutions for this one, E1 and E2. So among the two, we will then use E2 because when we are going to use it in the conversion, that will make much more sense because it will give us a positive conversion than the E1, which compared to E1 will give a negative conversion. So now in letter B, question B says that if the feed to the reactor contains equimolar quantities of methanol and acetic acid in no other species, we are asked to calculate the equilibrium fractional conversion. So as what I've said earlier, we are going to use E2, what we have found already, because it makes much more sense than E1. So equimolar means it has equal number of moles. Hence, if we choose an arbitrary initial amount like Na0 and Nb0 as 1, then as our initial basis, then we are left with this one, the fractional conversion, which is xa is equal to Na minus N0 over Na times 100, which is equal to extent of reaction. So 0.688 over 1,000 is equal to 68.8% fractional conversion of, yeah. And they're also equal since both of them are equimolar. So now for questions C, we are asked to, it is desired to produce 70 mole of metal acetate starting with 80 mole of acetic acid. If the reaction proceeds to equilibrium, how much methanol must be fed and what is the composition of the final product? So for this one, we can write first the initial values. So Na0 or initial value of A is missing, and then NC and ND will be equal to 0 since we assume that at initial amounts there are no product components generated or there are 0. So and NB is already given because it said that we are starting with 80 mole of acetic acid. So using this one, we then follow the problem statement proceeds to equilibrium. So we are going to use these equations we have found earlier on. So using this one, I mean for the equation number 1, the Na it is still missing because we still don't have Na0. For number 2, we can already for number 3, we can already find extent of reaction since NC0 is equal to 70. So sorry. Since we can already find the value of extent of reaction since the metal acetate is equal to 70 mole. So since we have already found number 3 as 70 mole, then ND is also equal to 70 mole because it is also assumed to be the ND0 is equal to 0. So now that we have the value of extent of reaction, we can also use it to plug in to find the value of 1 and 2. So for 1, we are still missing Na0, so we will still leave it like that. And then for number 2, we can already find Nb, it is equal to 80 minus 70 or 10 mole of B. So now, in order to find Na0, we can then use the equilibrium relation, which is given earlier. And then plug in all of the values. So we have already found NC, ND, NB, so we can put it there. And then Na is equal to this equation. So if we are again going to rearrange everything, then we will find that Na0 is equal to 170.6. That is the initial value. So if we are going to find the Na, then that was just going to be the Na0 minus the 70, which is equal to 100.6 of mole A. So if now you can then find the composition of final products, which is supposed to be the following: moles at equilibrium. We list it down everything, then the total, and then the mole fraction, which is equal to this equation, this one. So that one, and then we add it all together. That's also equal to 1, which is stays true to our assumption earlier that there is 1 mole for in this system. So that's it again.
Thanks. It's very for this. Okay. There are any question from the friend from the audience? Do you have any question, or you would like to how to explain more detail? Aside for this case, okay, this slide. And when you talk about the quadratic equation, we have possible two solution. The solution and negative and positive. This is the mathematics. That's right, but the mathematics. When you use in the real system, like for this case, you have to know the physical or chemical meaning. For this case, if you should write I'm not sure, right, 1.8. That's right. If you should psi 1, it maybe make your system is possible. It's not possible. Okay, for this case, only psi 2 0.688 is possible because it make positive conversion. If you use like 1.828, it make negative conversion. It's not possible in the real system. For this case, the mathematics and the real world, you have to consider carefully, right? Because there are possible two solutions for mathematics, but in the real world, only one solution, right, for the positive. Okay, I have one more question. When you talk about the question C, how many or how much the conversion of question C? Would you calculate the conversion of question C? From question A and B, the conversion is 80, but question C is not the same. Would you calculate the conversion?
The methyl acetate agent, right?
I think you have the number. Would you calculate quickly? I think the conversion of question C.
Fractional question C again.
Yeah. Conversion of question C. I think we have the information enough to calculate the conversion.
So if we're going to calculate it, then so fractional conversion of XC is equal to N C minus N C0 NC times 100. So NC is
It's better to calculate from like the reactant. You have A or B. That's right.
oh, okay.
That's right.
So NB NB0 over NB times 100. So 80. Oh no.
10, that's right. Okay.
10 minus 80. Wait, right. 80. I think this is negative. This is correct.
It should be inlet minus outlet.
Oh,
not outlet, but outlet. That's right. It should be 80 minus 70 divided by 80. We get about 86 or 87%. That's right. It should be the conversion is the inlet. Limiting reactant minus outlet, limiting reactant divided by the inlet, and then you multiply by 100%. For this case, outlet NA is 70, that's right, inlet. Outlet NB or outlet NA, NB is 80, outlet is 70. That's right, 70. It should be not 70, 80 minus 10, not 70. That's right. Because sorry, you're right. This is 80 minus 10 divided by 80. This is the inlet, that's right. This is the outlet. Okay. This is the conversion, or about 70 mole of B convert to the product. That's right. 70 divided by 80. Did you get the conversion? I think you calculate this conversion. I think it's about 86 or 87%, like this. Okay. Are you okay for this? You understand, right?
Yes, Ajahn.
Okay.
I think I got confused with the. Thank you.
Okay, so we stop the homework presentation. Thank you for your presentation.